Let's do another example here. Let's assume that f of n is the function 2n squared plus n, and the claim is that f of n is big O of n squared. How do we prove that a function is big O of some other function? Well, we need to show, or need to prove, that there exist constants c and k such that for all n greater than k, f of n is less than or equal to c times n squared. This is what it means for f of n to be big O of n squared. Some people ask me, what do you mean by constants, c and k? By that I mean that these two numbers should have nothing to do with n. Think of n as being the input length to a program. C and k cannot depend on n. They should be numbers like 100 or 1,000. So they stay the same as n is getting larger and larger. Okay, so we have 2n squared plus n. We need to show it's big O of n squared. Intuitively, this means that we need to show that as n gets very large, 2n squared plus n is less than or equal to some constant times n squared. So I'm going to choose my constant c to be 3, and I'm going to choose k to be 1. So what do I need to prove now? Well, I need to prove that for all n greater than 1, that's what we've chosen k to be, f of n, which is 2n squared plus n, is less than or equal to 3 times n squared. Why is this true? Well, certainly for all n greater than 1, n is less than or equal to n squared. So that means, this implies that 2n squared plus n is less than or equal to 2n squared plus n squared. But this 2n squared plus n squared, this is equal to 3n squared, and that's certainly less than or equal to 3n squared. So there you have it. We have f of n, which is 2n squared plus n, and we've exhibited a constant, namely 3, such that for all n greater than 1, that was our k, 2n squared plus n is less than or equal to that constant 3 times n squared. So this implies that f of n is big O of n squared. Very crudely, you can read the big O as a less than or equal to. If f of n is big O of n squared, it means that f of n is less than or equal to some constant times n squared, again, for n sufficiently large. Let's do one more, slightly more interesting example. Let's assume that f of n is n factorial, and I want to prove that f of n is big O of the function n to the n. Okay, so my claim is that n factorial is big O of n to the n. So what do we need to prove? We need to prove that there exists constants c and k such that for all n greater than k, n factorial is less than or equal to c times n to the n. So I'm going to let c be 1, and I'm going to let k be 1. And I need to prove that for all n greater than k, which is now 1, n factorial is less than or equal to 1 times n to the n. Why is this? Well, n factorial is n times n minus 1 times n minus 2 times dot dot dot, so on and so forth, down to 1. And this is certainly less than or equal to n times n times n times n n times, right? Every I have n here, and then I have n minus 1 on the left-hand side, but I have n on the right-hand side. I have n minus 2 here, and I have an n. Every term on the right-hand side is bigger than every term, greater than or equal to every term on the left-hand side. So therefore, this quantity is less than or equal to this quantity. So this implies that n factorial is indeed less than or equal to n to the n, and so choosing the value of c here of 1 actually makes sense. I mean, we've proved that n factorial is big O of n to the n, because we know that for all n greater than 1, n factorial is less than or equal to 1 times n to the n. Now another slightly interesting thing we could do is, since we know that for all n factorial is less than or equal to n to the n, we could take the log of both sides. We get log of n factorial is less than or equal to n log n. And this implies that log of n factorial is big O of n times log n. Because for every n, log of n factorial is less than or equal to 1 times n log n, so therefore log of n factorial is big O of n log n. Here's a really simple example, but still worth mentioning. Let's say that we have the function f of n equals 100. It's a constant. So for any input length, or for any number n that you put into f of n, you always get 100 out. Claim is that f of n is big O of 1. Usually you see like n or n squared or 2 to the n inside here, but f of n here I'm going to say is big O of 1. So why is that? Well, remember, we need to prove that there exists c and k such that for all n greater than k, f of n is less than or equal to c times 1, because we put a 1 in there. So I'm going to choose my constant c to be 100. And k, again, we'll pick to be 1. So then we need to prove that for all n greater than 1, f of n, which is 100, is less than or equal to a constant c, which we chose to be 100, times 1. And you can see that n doesn't appear on either the left or the right-hand side, but that's fine. For all n greater than 1, it is definitely true that 100 is less than or equal to 100. In fact, 100 equals 100. So this implies that f of n is big O of 1. So just another way of saying that f of n is a constant. You know, if I'd put 1,000 here, or 10,000, or 100,000, or 1,000,000, any constant that doesn't depend on n, so f of n is a constant, that function, in that case, if f of n is a constant, then f of n is big O of 1.